Okay, hi. This is Friday, the 20th, I guess, of April. This is session 41 of AE 554. And as I told you last time, again, we have another guest speaker today. Today is Mr. Jim Harder, who's going to talk to us about AFGROW. Jim is a Purdue graduate. He got his bachelor's and master's degree here. Got his master's in 1980. In fact, Jim was the first master's student that I worked with a long time ago. In fact, he took this class the very first time I taught it, which I think was probably fall of 80 maybe, or spring of 80. But at any rate, Jim is, has had at some point in time you'll be old like the two of us, and maybe at some point in time, maybe you can come back here and teach a class. But at any rate, Jim worked with Northrop for a couple years, and then he worked with Sikorsky for a number of years as a stress analyst. But then he's been with Wright Laboratories. I want to call it Flight Dynamics Lab, and I know that's not what you call it now. What do you call yourselves now?
It's the Air Vehicles Directorate.
Air Vehicles Directorate. You know, some names, they'll never teach an old dog new tricks, and I'll never remember that. But anyway, Jim has been with them for 25 years. And one of the things that Jim has made a significant accomplishment for is writing a multi-purpose fatigue crack growth program called AFGROW. It's a very powerful program, and it's, as I indicated to you before, it is described in the appendix of our book, an old version of it. But what Jim's going to do today is to give us an overview of AFGROW, demonstrate how it works, a very powerful fatigue crack growth program. Sometimes when Jim comes to class, I embarrass him by showing old photographs of him, and I don't have those with me now, but I did on the web page. I posted a couple of slides for this class, and there's a picture of him a long time ago as a student. But anyway, with no further ado, here's Mr. Jim Harder.
Thank you, Skip. It's great to be back here. Professor Grandt tells me this is Grand Prix weekend. Is that right? Do you still have the go-kart race? Okay. Can everybody hear me okay? All right. Now you guys did some crack growth calculations, writing some kind of a code on your own. Is that correct? Okay. Now imagine, we did too when I was taking the class, and imagine if you took that homework assignment and went completely nuts with it, and then you end up with AFGROW. That's what kind of what happened. In AFGROW, I like to think of AFGROW as a framework, an analysis framework, or a toolbox, if you will. Sometimes I think people make a mistake when they think about they get an answer for a life prediction problem, and they say, okay, that's AFGROW's answer. Now, there's other codes. There's NASGROW, built by NASA, as you can imagine. There's CRACS, University of Dayton, came with a code called CRACS. I don't think that's still in the market. It might be. I apologize to them if it is, and I said it wasn't. There are codes that do fatigue. And now, AFGROW does crack initiation, but it does it with your basic strain life. And if you guys use strain life in class, it uses a very simple strain life algorithm. There's a code called ENCODE that was put out in the UK that's quite sophisticated. It works with the Finite Element program, and that's also on the market. I can't remember how much it costs now. But anyway, I'm going to tell you about how to use AFGROW. I'm going to show you all the different steps. When you do a life prediction process, one of the first thing you do is you look at what's my geometry, right? So if in AFGROW, and again in AFGROW you don't have to do anything in any certain order, but logically, I would say if I go to one of these shortcuts that I can pick my classic models, for example.
So Jim's already loaded AFGROW. He's got it on his laptop, and he's already loaded it, so he's ready to go here and demonstrate.
Right. And if you pull up the classic models, there's a number of solutions you can find in either handbooks or in published articles that are very, very commonly used. You'll see here, you have different part-through cracks, corner cracks at a notch. We can have a corner crack in a plate. Here's what's called a surface crack in the plate, and so forth and so on. You can see down through here. And then once these cracks, that are part-through cracks, will transition at some point to go through the thickness, then you'd have to have the corresponding through the thickness model, which you'll see here. You could, start with either one, of course, and if you pick the through crack, of course, then it would only stay a through crack until failure. Now, one of the things that you guys did, or the thing you did in class, I guess, was the embedded crack. that correct?
Last homework assignment, they were supposed to write a cycle-by-cycle code for embedded elliptical.
Okay, in your case, it was an infinite plate. Okay, and I always joke around about this, and when you do discrete stuff, you can never find the infinite plate when you need one. And so now I'm going to have to say in this, we're going to have to go to the dimensions tab, and since I can't make it infinite, let's say we'll make it 10 by 10. In this case, I said that the width was 10, the thickness is 10. And let's say I made my flaw, say, a circular 05 by 05. Now, I also can go here to the load tab because I have the different solutions. Well, in this case, I only have the tension case. In some of the cases, you might have bending, or you might have bearing if it's a hole or something. In this case, there's only one choice, so we got the tension solution only. And now when we say apply, then you'll see a picture of what you just did. Now, we have a 10 by 10 block, and we have a 0.05 by 0.05 crack, so you can't even see the crack, right? So I'll say OK. And then if I want to take a look at the crack, I can zoom in and zoom in on it. So now we've taken this 10 by 10 block and kind of made it sort of like an infinite plate. Okay, so that's the one step, is now we got our model we're going to use. Now, besides the model, I want to encourage anybody to speak up, so please don't be shy. What else do we need to know besides the model itself to do a life prediction? Anybody? How about the loading? So we're going to apply some kind of loading, right? So in AFGROW, I'm sure like in most other codes too, we can either go to our input and we can pick spectrum, or we can go have shortcuts, but we'll go to the spectrum, and there's several choices. I can use these pre-canned normalized spectra where your maximum is 1, so then I can scale it by using this, what I call the spectrum multiplication factor. And that's kind of what I'll do here. I'll make this to be, let's say, 16, and I'm in the English units by default, so this will be KSI. And we have here the ability to look at residual strength requirement. Let's say you had a structure that you had some kind of a loading spectrum, but it was variable amplitude, and you had some maximum that you would have to maintain at some point. Now, but you may not know when that maximum is going to occur. So to protect yourself, as AFGROW goes through the analysis, it goes through the sequence of loads in the spectrum in order. But if you didn't know when the max would occur, you'd want to always check at every step to see if it happened now, would it fail? So that's the significance of this. If you put the stress value here, that tells AFGROW, I want to check every step of my analysis to see if that load would fail me, even if my applied load at that moment might not. Does that make sense? That's what that's for. Now, the other here is stress preload. You could have a case where, due to fit up or something, that you have a preload on the part, so you want to then superimpose that on top of your applied load. We won't use either one of those, but I want you to know they're there. Now, the simplest thing we can do is we can pick a constant amplitude loading here. We could open a spectrum file that pre-exists or you created some other way, or we could go through a little wizard to create one, but in interest of time, I'm going to pick just a constant amplitude spectrum, and we'll say, okay, so we said it's constant amplitude, but that's not quite enough information. We need to know what's our max and what's our min. So if you've talked about the stress ratio. So R, again, is the min to max ratio. So that's how AFGROW does this. If we said 0, that means your min is 0, your max is 1. If we would say 0.5, then your min would be 0.5, your max would be 1. Your max is always going to be 1 in this case. So your R and your min are the same thing. Then I say, well, how big is the block? By default, we'll just say 100 cycles. We can change that. If you expect your life to be quite long, AFGROW repeats 999,999 times through the spectrum. But if that wouldn't be enough, you might say, well, I want to make this block 1,000 or 10,000. But it just keeps repeating whatever block that you give it here. So for now, we'll just say 100. And we have time-dependent capability. I don't have time to talk about that, ironically. But let's go ahead and we'll say, okay, now we have a spectrum. And if we want to look at it, we can go to View, Spectrum Plot. It's not a very interesting plot, but it's going from 0 to 1 100 times. So we will close that. Okay, so anybody else? Now we've got a model, we've got some loading. What else do you think we need to know to do a life prediction?
Material properties?
Yes, need material properties. So we need to say, what is this made of? Now we can go to, again, input, material. We have different material relationships that we can use. Now you've probably talked in class about, I would think you probably talked about all these, I would guess. You've talked about the Foreman equation. I don't know if you talked about my T method or not, but that doesn't matter. The AFGROW equation, perhaps, you might have talked about that. The table lookup is my preferred way, or the Walker equation. So just in the interest of making something, I guess, simple, let's just look at the Walker equation.
Professor, could you move your mic for us? It's rubbing on your collar.
Oh, sorry. Let's see. Is that close enough? Will that work? Okay.
Yeah, thanks.
Okay. All right. Now the twist here is this is a Walker equation, and you'll see there's a room for several different inputs. That's because if I can go to the paper here for a second and just show this. I know you've probably all seen this before, but if I was to look at your crack growth rate versus delta K, you know, typically you'll see for aluminum, you got to look at that double turn here. A lot of times this area here is represented by a straight line in log-log scale. That's where you get that the ADN, the Paris equation, equals C delta K to the n. That's that straight line, and this is log scale over here. That's where that comes from. The Walker equation just takes and allows you to account for the shift that occurs as a function of your stress ratio. And that shift has to do with what is going on with your opening levels and things like that. But since we're trying to model something that looks fairly sigmoidal in shape, one straight line is not going to be enough to characterize your material throughout the whole range of crack growth rate. So you might say, well, I could do a line here, 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 do a line here. You know, I could do 5 lines instead of 1 line or 2 lines. Whatever I thought that I could use best to characterize the material properties. Does that make sense? That's why in AFGROW you'll see these 5 different possibilities of your slope and your n and your m values. That's what that's for. I'm going to just take the defaults as some typical aluminum type property, along with your yield strength and your Poisson ratio, Young's modulus, and your fracture toughness values. You know, you talked about plane stress and plane strain fracture toughness. Okay, well here you see you'll put your plane stress fracture toughness is here, your plane strain is here. You can obviously change these. Down here you'll see it says delta K threshold value at R equals 0. That just tells you at what value and below that you would predict that you wouldn't get any growth. And we do that at R equals 0 because there obviously would be a 1 at any R you would be at, but that is I guess that's a standard way of doing it. Now I'll say OK. Now we've got a material, we've got a model, we've got loads. If I wanted to look here in this window, I want to look at our crack growth rate data. Well, there it is. There's that straight line. We had one segment in log-log scale, and there we are. And now I can expand this if I want to see it a little bit bigger. And if I wanted to look at what the effect of R is, I can just simply grab this tool and move it. Or if I click right here, I can type in an R, say 0.1, enter, and it will go right to whatever that model would give you at R of 0.1 or whatever else it is. So this is showing you what AFGROW is going to use internally as it goes along in the life prediction process. Okay, any questions about any of this so far? All right. So as I said, we've got our model, we've got our material properties, we've got our loading. Now I'm going to go zoom in on this a little bit more. We'll probably go off the screen here. But when we hit the run button here to do the prediction, AFGROW, as it does a prediction, it will show you this crack here, which you see in the black. In the plane, in the crack plane, it will be growing, and you'll watch it grow. So let's go ahead and do that. Whoa. So it's growing. Now I can go to View, Zoom, go back here to no zoom. Well, something happened. It didn't stay circular. One side popped through first, and it went this way. Because we have different corrections for the width and different corrections for the thickness, so it's going to pick up one faster than the other. Obviously, the thickness, the effect caught first, so it went through. When I look at the output here in the bottom window, and probably too many output lines, once you reach a level here, the buffer is full, so you lose what was before it. But I'll show you a little bit later how you can take care of that. But what I want to show you right now is you have the printout of the A length, the C length, the A length, your beta values. By the way, beta values, is that something that you're familiar with? Okay. And we have our R's. Your R's in terms of K. When I say RK, that just means my K min over K max, which could be different than my S min over S max, especially if we have retardation models, which I haven't talked about, but I'm sure you guys have talked about retardation models. We'll talk about that too in a minute. So that gives you all your output information. Now, before I do something else, because I mentioned this, I can go to this predict window and I can look at the preferences. One of the things that when people use AFGROW, sometimes they overlook the preferences, and they're kind of important because preferences are where you tell AFGROW how to handle certain things. For example, if I wanted to look at my growth increment, when I go to calculate a stress intensity factor for a given model, in this case, it's a canned set of equations to calculate the stress intensity. Sometimes that could be kind of numerically intensive, perhaps. So if you had a large spectrum and your crack growth was 10 to the minus 7, 10 to the minus 8 inches per cycle, you may not need to calculate that K every single time, because the difference between K as you grew 1 times 10 to the minus 8 inches is not going to be very large, right? So you might be wasting computer time. So what you do here is you say, well, how often should I go and recalculate K? And the default is 5%. So at 5% change in crack length, it will go back in and recalculate the beta. And that means, and that's a moving scale. So now when the crack is 1/10 of an inch, it's 5% of 1/10 of an inch. When the crack becomes 1 inch, it's 5% of 1 inch. So it keeps updating that increment every time. So you can make that about anything you want. You can go anywhere from cycle by cycle up to, I think we stop you at about 15%. When you get above 10, we'll give you a little warning that you might be a little going overboard here. But then you can compare your answers and say, well, what's the difference in answer versus the difference in my runtime? That's what that can do for you. Now we look at our output intervals. How often do we want to print out our output? Do we want to do it, in this case, the default is at specified crack growth increments. And if so, here, what is the increment? And this default is 0.01, and we're in English units, so it'll be inches. I could say, oh no, I want to do it at a cyclic interval. So then I'll say, well, how many cycles do I want to wait between outputs? So you put those in. Or I could pick after every spectrum stress level. So in that case, if you're planning on printing this out, if you have a big spectrum, you might need to have a lot of paper. But otherwise, that's good for debugging, I would say. But otherwise, you probably want to stick with one of these. Now, output options. I mentioned before that sometimes you can overrun the buffer. If you overrun the buffer and you want to go back and you want to see output, or you maybe even want to save it in a file to look at later, well, the default output goes to the screen, but we can go to a data file, which is a text file. We can go to a plot file. And the difference between a plot file and text file is simply that the text file has headers at each output line to tell you what is what. In a plot file, you don't want that because you want to maybe bring it to Excel. You don't want to have headers every single line to sort through when you want to plot something. So the plot file is a text file without the headers other than just at the very top. We also have an XML file. If you wanted to print out with tags that we have in AFGROW for different values, then you could use some kind of a template to print out a form, let's say, that you wanted to format it in some way. But that's what you have an option of doing also. I guess there's not much more to talk about here, but there's more things you can do with this. Now we have propagation limits. If I wanted to stop at a given crack length, I could click here and say, okay, what crack length do I want to stop at? In this case, it would be the C length, the length through the width that you want to key on. A cycle count. In this case, the default is Kmax, or when do I exceed my fracture toughness? Or a user-defined value. If I want to say, well, I want to put my own Kmax value, and if I exceed that, I want to stop. And I also have net section yield. You notice that these are boxes, so you can check more than one. And it will stop you at the first indication, or at least will print out you would have failed here based on this criteria. Or you want to say, oh, no, stop when the transitions to be a through crack. So those are the kind of options that you have. You can see you have other options too, how many times you repeat and so forth. And then the transition, I can say I transition to a through crack when I've gone, in this case, 95% of the thickness. You can see I could change that to whatever I'd like. I could also say whenever Kmax in the A direction exceeds some value. That's another way of predicting transition. And finally, if you're doing a lug problem, we found that if you had the different boundary conditions for the lug loading, the bearing loading, it has quite a different result, so you can then change how you handle that as well. So I guess the thing to notice here, it's a very flexible tool, and you can do pretty much whatever I think you'd like to do. And if you find something you would like to do and you don't do, just let us know. We'll do our best to accommodate. But that's what that's for. Okay, so we saw that. Now, we had, I'll go back and I will bring it back to the beginning. There's our inertial crack again. Now, it's just easy enough, as you saw. I'll go to the dimensions. I can make the C be twice as big. There it is. Now I can do that prediction.
Can you stop this one when it gets a little bit bigger so we can...
I'll try to stop it in time. Let me go. I'll turn the zoom off. That'll help too.
The thing we should see here is this one will want to go to a circular crack. But it did right away.
Mm-hmm. Yep. So yeah, it's going to try to do that. And then as it gets closer to this thickness, it's going to get a thickness correction. It's going to kick in, and that's why it happened the last time. As we keep going, it said, "Oh, I popped through. I got to I guess in this case, I got to a K value that exceeded the toughness, and it went. Now I've become a through crack." So that's how that works. So any questions about that problem? And you guys, when you did your prediction, did you pretty much see the same thing, that you had a different shapes and they tended to become circular? Yep. Okay. Again, any questions at all, please don't hesitate to ask. If I go back, actually, you know what? I think we're going to run out of time. I'm going to go to the advanced models. Now, in AFGROW, we can also do multiple cracks. Right now, we can do 2 cracks anywhere in this plate. Pretty much. I'll explain how that works. For example, here we have different objects. I don't know how well you can see this, but we have a hole, we have a countersunk hole, we have a through crack, a part through crack, and a slot. So if I would say, for example, take a hole, drag it onto the plate, drag another hole onto the plate, let's drag a through crack on the plate, and drag another through crack on the plate. I can just put them there. I could take them and dock them to a hole, so that becomes a crack at a hole with an internal crack near this other hole. Whatever you'd like to do. Probably more typically you might take a corner cracks, but let's take these 2. I'll dock them both to the hole, but now I'll make one a little bit bigger. Now, that's kind of hard to get exactly where you want, right, when you're doing with the mouse. So what you can do is, anytime you click on any object here, I clicked on the specimen, and you go over to your specimen properties, and your properties, you'll see, well, it has a width and a thickness, and those are the properties assigned to the plate itself. If I click on a hole, well, now it tells me the hole, its diameter is 0.4 by default, and its offset is 2.849 inches from that left edge. Now, if I click here, it tells me this hole is 0.4 and its offset's 1.457. I could click there and just put 1.5, moves it. If I click on just the crack alone, it says, oh, here's my crack, and it's 0.508. I want to make it 0.5. And then I click here. That's 0.2. I'll leave it alone. And I will go and look at my crack growth curve. And I can erase what's on there right now. And I can run it. So it does a prediction with both of those cracks. I can, of course, go in on any object I want. And I can hit the delete button and remove it, remove the hole, whatever I'd like to do. So we try to make it fairly intuitive to use. So that was how you say you'd want to look at a couple cracks. Now if I want to look at, say, corner cracks, I could take this corner crack, put one here. The way this works right now is we can only have these corner cracks at one of the holes. But that doesn't mean I couldn't have another hole out here someplace that the one crack is growing towards. It's just that you couldn't have one corner crack on this hole, another corner crack, because we just don't have that solution. As it stands right now, the matrix in here, these have all been solved by finite element models. So we have different crack shapes, we have different hole diameter, plate thickness, we have all kinds of, so the matrix is quite large. So to expand it to do any number of combinations of one on one hole, another one another hole, it starts to become unwieldy. But anyway, we can solve this problem as well. I'll erase this. It takes it a minute because it has to load the solution, and now it's going. And it gives you the A and the C. In this case, it's A11 and C11. I could easily have plotted the second tip wherever one I wanted to plot.
Which crack is that?
This one is, 1 is going to be the leftmost one, and 2 will be this one. I can go in here, and I can tell it to plot A12, oops, A12, and C12. There, now it shows both of them. Shows both C's and both A's overlaid on the same plot. Now if I click on this button here, it says overlay, and I wanted to say what happens if I go in here and say instead of 16 KSI, I say what would have happened if this would have been 14 KSI. I don't know, I'm just pulling that out of nowhere. Oh, okay, well there's your plots at 14 KSI. So you can compare different scenarios and see which one is better, worse, or whatever you'd like to do. All right, so I showed you kind of how to do these cracks. I can go back to our classic model again, and I'll pick, let's say, the standard corner cracked plate. I'll take the defaults, and I'll erase this. Now this solution, if I could have done this with the advanced model, but I would have gotten a different answer. And the reason for that is because these classic solutions, in this case, the classic solution for a corner cracked hole has been taken to be the Newman and Raju. I don't know if you ever heard of the Newman and Raju solution. That's what this is. The other solution that we were using came from Dr. Scott Fawaz and Bori Anderson did a more recent study where looked at these multiple cracks, and they have a tabular solution that's, again, that very huge matrix. It's not exactly the same as the Newman curve, because this is a curve fit, actually, to Newman's older numbers. But, okay, so now I've already got a material property put in there. I could choose, for example, let's do something different. I can say, well, let's take table lookup. Now, when you do table lookup, the thing that I want to show maybe on the paper, I'll just do it here. We talked about it, but we have our rate and delta K. Now, if we're going to have table lookup, we pick points somehow that we choose so that if we were to draw, say, a straight line in log-log scale between any 2 points, that we would be happy with the accuracy that we would get. But now, if I pick whatever points I want to pick, in this case, I can I can choose up to 30 different crack growth rates, and I can choose here up to 10 different stress ratios. Now, I don't know if you guys have you looked through any of the literature to see what data might be available to you to do a life prediction if you go to the open literature? Well, imagine that if we're down here at 10 to the minus 9 inches, I always work in English units, I'm not very progressive in that way. If we go 10 to the minus 9 inches per cycle, and if we're running a test at 10 hertz, and let's say that we're trying to measure cracks every 100th of an inch to kind of minimize the amount of scatter, think how many seconds that would take between each data points you would collect, and so how long it would take to do the test. So it's often difficult to get a lot of data in the literature. Sometimes if you're lucky, you might get data down to 10 to the minus 7, and maybe you get data 10 to the minus 3. Most of the time you'd say that was a good day. You know, if you can get data down below 10 to the minus 7, it's wonderful. Sometimes you end up having to use data that you found for a similar alloy to give you a clue of where it's going, because you oftentimes won't have it. So the reason I'm mentioning this is because we say we can use up to 10 different stress ratios, but if you're looking at real data, chances are you may not be able to find that many different stress ratios, right? But the point of it is, if I'm going to find out what my crack growth rate curve might be doing when I'm at some R other than the R's that I have got data for, how many, at the minimum, how many curves would I have to even make a guess as to what the data would do? At least 2, right? I mean, 1 would not tell you anything. At least 2, you could, extrapolation is not easy, but you could at least interpolate between and try to extrapolate beyond in some intelligent way. So you have to have at least 2. So that's a long drawn-out way of explaining that in AFGROW, when you're using table lookup, you'd like to have at least 2 R's. Now you don't have to. AFGROW will run with 1. But what do you think would happen if you just put 1 R in and you did a prediction for some spectrum? You wouldn't get any effect because it wouldn't know what to do. I mean, you could put it in and just realize that whatever I put in there is going to be used at all times no matter what the R is. So you have no way of differentiating the effect of R if you only use 1 curve. That was the reason for that long drawn-out explanation. Okay, so the default here that we come up with when you pick the table lookup is this kind of a standard aluminum alloy. I think it's probably a 2000 series alloy. I can't remember. These are just made-up numbers that are close to what we see in test. I say, okay, now if I go over here and look at the plot, that looks a little different than that straight line you saw before with the Walker equation. So I can take 0, I can freeze that curve, that's the thermometer there, by the way, and I can go to a different R, freeze that curve, and go. So I can see how these data look and how it's, and if you want more details on how the extrapolation and interpolation is done, it's in the user's guide. You can go online to afgrow.net and you can look at the manual if you're interested in it. But that's kind of what you need to know to be able to extrapolate and interpolate the data. Okay, no questions about any of that? All right. Go back to the crack growth rate curves. I will leave the overlay on. And this time, I think what we'll do is we'll do something different. We'll talk about spectrum. I'm going to increase this to 25 KSI because I want to use a spectrum called the Falstaff Spectrum. So I'll open this up. And I have to go to the AFGROW directory. And there's my Falstaff Spectrum. Now I have it, and I can look at it. Now that's a little different. Now these colors have significance, but these colors up here mean are that we have divided this spectrum into 5 different files. This was kind of legacy from when computers weren't able to handle as big of files as they can now, but we've broken this up into 5 files. There's, as you may or may not be able to see, it's 17,983 cycles in the spectrum. If I zoom in on an area here, I can take a closer look. And these colors represent flights. So within this spectrum, we have subspectra. In this case, we call them their flights. And you'll see them differentiated by different colors here. So you can see the airplane did some maneuver, came back, landed, another flight, another flight, another flight. There's 200 flights in the spectrum in total. Have you talked about exceedance curves? Okay, well I can also look at exceedance curves. So I want to see how many times does the minimum occur, how many times does the maximum occur in the spectrum. It gives you an idea of whether or not you're spending a lot of time with high loads or low loads or in between, and gives you a way of characterizing what the spectrum kind of looks like. So that's what you can do also with AFGROW. Okay, so now we've got a different spectrum. We have 25 KSI maximum, so it's everything in that spectrum is multiplied by 25. I'm going to run it. Boom. Now, let's say if I went back here and said, well, what if it was 20 KSI, like we did before? Okay, fair enough. But if I erase that, what about, I'll run it again, what about retardation? We saw that there was different loads here, right? You talked about retardation models. Well, in AFGROW we can go to our retardation models and we can pick from what we did up to now was no retardation. We assume no effect of previous loads. We have a closure model. We have the Dr. Newman's fast-tran model. We have the shoe model that Lockheed has used for years. We have the Wheeler model, which is Boeing's used historically. And we have this Willenborg model, a generalized modified Willenborg model that you can pick from. Well, let's take a look at, a lot of people use the Willenborg model. Let's use it. Now for aluminum, typically I will start out somewhere around, close to 3, let's say 2.8. What that means is what overload would it take? So if I had an overload, it was 2.8 times my nominal load to essentially stop the crack. That's what that parameter is supposed to be. So we say, all right, we'll say all right, and I will then run that. So that was the green line, is the new run. So we're saying that this spectrum that we saw would then result, if we accounted for retardation, we might get a little bit more life because of these overloads that you see occurring every so often compared to these other lower loads that happen in between. So that's what that can do for you. I could choose any of the other, the closure model, you can go on and look at the manual to see how they work. But that's a quick overview of the code. Now, I don't know if there's anything else you'd like me to show? Or?
Well, I think you want to mention your units.
Oh, yes.
Switch back and forth.
Oh, sure. Okay, thank you. One of the things we can do, if we go to the status view, and I open up the area where it talks about my specimen dimensions, my crack length, and that sort of thing. And I told you I wasn't very progressive in how I deal with units. Oops. I'm going to try to. There. Down here, if you can see it, it says English. If I hold the mouse over here, it doesn't work. Okay, well, I can choose metric. And when I click metric, what happens over here now, all my lengths are going to be, anybody want to make a stab at it? What do you think that would be in the metric system? Meters? Meters. Now people ask sometimes, the reason I said people ask sometimes, why don't you use millimeters? Because a lot of people, when they do crack growth in the metric system, they will use millimeters because it's more suited towards these 0.5-inch flaws. And then we don't, because we try to be consistent with our SI units, because sometimes when you convert from one to another, if you do your crack length in millimeters, you do something else in meters, you're asking for trouble. We keep everything consistent. And my only answer always is to that is, well, you're the guys that say all I got to do is move the decimal point, so just move the decimal point, and that's good enough. So your crack length in AFGROW and metric is always going to be meters, so always consistent. Megapascal, meter, and degrees Kelvin. And if you wonder why we have temperature there, it's just because we used to historically we had a bonded repair capability where we had composite bonded patches that were cured under temperature. So we were concerned about the differences that happened to the thermal expansion, so we had to include temperature. But so I can switch on the fly, which means also that if I look at my crack growth rate data, I'm in metric, now I'm in English. Metric, English. We can do that all day.
And you can enter numbers in different units.
Right. So let's say I had some data in English units, and I wanted to go into my table and I wanted to enter those data, and then I had other information in metric. I could then go to metric and switch. I'll tell you one little story though. I gave a demo one time at a pretty big meeting. I think there were 600 people there, and I was showing how neat this was, that you could switch between metric and English units. And I ended the presentation, that part of the presentation, on metric. I closed AFGROW. And then I opened up what AFGROW also can do. It can do automated analysis, so I can go into an Excel spreadsheet and I can set up a problem in Excel, and you won't even see AFGROW in the background, but then Excel can call AFGROW and say, here's my geometry, do a prediction and give me back the answer, put the answer in cell B3. Well, that's all nice, except for the way AFGROW does things. When you close AFGROW in metric units, and then if your code you wrote to tell AFGROW to do an analysis doesn't tell AFGROW, hey, I'm in English units, I just forget to tell it what units I'm in, it's going to do what? It's going to say, oh, last I knew I was in metric units. So I had a problem where I put a crack of like 1/10 of an inch or something. And AFGROW thought when I hit the run button that it was 1/10 of a meter, and it immediately failed and nothing happened. So I'm hitting the go button in this demo, and it doesn't work. And I had rehearsed this, and so I'm in front of 600 people thinking, this really worked in the hotel room this morning. but it was because I had closed it in metric units. So whenever you close AFGROW, whenever units you close it in, when you open it the next time, it's going to be wherever you left it. Same pretty much goes for your windows. When you size your windows or anything else, it remembers what they were, how big they were relative to your screen and all that sort of thing. So that's how that works.
One thing we want to make sure we do is availability of the program.
Oh, yes.
And your website.
Okay.
Put your web number down.
Yeah. Okay. Well, it's very easy. I'll write it down right here. If you can read my writing, I'll do it in caps. AFGROW.net. I work as a consultant on a part-time basis because the Air Force no longer supports, maintains AFGROW. So now a company called LexTech does. I work for them part-time. So they have a special student deal if you want it, but that's available to you. We also have a lot of other information. If you're familiar with the Damage Tolerance Design Handbook, for example, if you want to look at that, that's on the web page. It's all accessible there. It's free to use, look at. There's a material database you can go to, and you can, of course, to get access to the data, you have to be a customer, but you can actually browse through and see what material data are available in the database. So that's all there as well. So like I say, this started out as a 554 homework assignment, and it's ended up as a little different. So any other questions or anything? Demonstrate. I showed, well, maybe I could show the automation. All right. Let's see. I'll go to Documents, AFGROW. Let's see. Go to Class. And okay. Oops. Shift A. Well, now, oh, I see why. Okay. Let's suppose I said I wanted to run 50,000 cycles, and I want to get my answer within 50 cycles of it, and I want to allow it to iterate 30 times. AFGROW's running in the background. This is just a through crack example, but it tries a number, says, oh, that's too big or too small, tries another number, and just runs automatically till it figures out what the crack size had to have been to give me the life I was wanting there. So you can set up macros that can run AFGROW in the background. You can do any number of things. You can do Monte Carlo analyses, all that sort of thing. So there's a lot of things that maybe not be obvious when you just look at AFGROW itself on the outside. So one guy says it's more than just a pretty face, I guess.
Are there any other questions anybody has? Jim, there's lots of ways of doing things.
Mm-hmm.
The different retardation models. And when
Right.
you're in a real problem, how do you decide which is the right way to do your particular problem?
Well, okay, for me, it comes down to, I guess, personal experience. One of the things, you kind of know, retardation models are far from perfect, right? And so over the years, people have used the Willenborg model and become comfortable with different shutoff ratio numbers. Like I mentioned before, aluminum, some usually around 3. Steel might be around 2. Titanium might be around 2.5. That's just kind of rule of thumb. But then what you usually do is you say, well, I'll run a couple tests and I'll see if I can figure out what works out. And then you'd like to believe that that number is a material property, that no matter what happens, I can do, but that's not the case. If I have a spectrum that had a lot of compression in it, for example, it might do a little bit differently than if I had one that had a lot of tension or any combinations of the things. So unfortunately, it's not always cut and dry. From my experience on tests that we've done in the lab, for transport type spectra, we found, and some fighter, we found that the shoe model, just with the standard parameters, default parameters, worked pretty well for us. That doesn't mean it works for everybody all the time. We found good results with it. The closure model works pretty well, except for cases where if you have a lot of high R stuff in your spectrum, it tends to not do so well. So that comes a lot from experience. Like I said, those rules of thumb for the Willenborg model are a good starting point. I get nervous when I hear people using a Willenborg model and they come back and they tell me that they used a shutoff ratio of 1.7 to get a number to work out the test. Because what you're doing is you're saying, well, I'm picking this crack growth rate model, this material property, for my prediction, and I'm changing my shutoff ratio so I get the answer that the test showed. How do I know that your crack growth rate model was any good, for that material? And now we're tweaking a parameter over here to get an answer we want over here. And if that parameter doesn't make sense, like a 1.7, then you got to ask yourself, maybe there's something else that I'm doing wrong, But I'm not sure that answered your question, but that's kind of how I do it.
Experience and test results.
Yep, right, experience and test results. That's the short answer.
Are there benchmark cases that are published that one can go to?
The Damage Tolerance Design Handbook has data. The material database, the fracture mechanics database we have, has some crack length versus cycle data. ASTM has published round robin results over the years where we looked at the it was this I think it was a Falstaff Spectrum and it was a transport spectrum, and those are all available. And I've got those too. If somebody wants them, I can send them to anybody with those results. Those were corner cracked holes, by the way. So, thank you for having me.
Well, thank you very much. I very much appreciate I very much appreciate Jim coming back. He does this fairly regularly, and it's a very powerful tool that he's developed. Well, that's class for today. Thank you.